Good day, everyone. We are from Group 2, and we are going to discuss about differentiation. Let us work together, do our best to learn as much as we can, respect and support each other through all the challenges. Our objectives for today's lesson is history of differentiation, application in Mindanao context, solve problems such as delta method, algebraic product rule, trigonometric quotient rule, exponential or logarithmic higher order derivatives. Tips for future basic calculus learners and references. History of differentiation. The concept of a derivative in the sense of a tangent line is a very old one, familiar to Greek geometers such as Euclid, Archimedes, and Apollonius of Perga. Archimedes also made use of indivisibles, also, although these were primarily used to study areas and volumes rather than derivatives and tangents. The modern development of calculus is usually credited to Isaac Newton (1643 up to 1727) and Gottfried Wilhelm Leibniz (1646 up to 1716), who provided independent and unified approaches to differentiation and derivatives. Newton and Leibniz essentially created integral and differential calculus. They were both interested in objects that are in motion; however, they both look at different aspects of these. Newton was more involved with the speed of a falling object, and Leibniz with the slope of curves to illustrate the rate of change. These are the portraits of Euclid, Archimedes, and Polonius of Perga. Although they both looked at different things, they both came up with the same results, hence the accusation of plagiarism. However, combining both of their ideas, a fundamental theorem of calculus was created, which links the concept integration to derivation. Those two weren't the only ones who contributed to the discovery of calculus. There have been many other known mathematicians of that time that also helped with the development of calculus. René Descartes indirectly helped create differential calculus by introducing variable magnitude. Nevertheless, Newton and Leibniz remain key figures in the history of differentiation, not least because Newton was the first to apply differentiation to theoretical physics, while Leibniz systematically developed much of the notation still used today. Since the 17th century, many mathematicians have contributed to the theory of differentiation. These are the portraits of Isaac Newton, Gottfried Leibniz, and René Descartes.
Application of derivatives. Derivatives have a wide range of application. One of its example application of derivative is business. Companies today, such as the Temple Company in Butuan, use derivatives to chart the data that has been charted on a graph or in the table, such as Excel. Once it has been entered, the data can be graphed, and derivatives can be used to estimate the profit and loss points for specific ventures. Also, derivatives in business can also help in minimizing and maximizing profits because we were able to chart the data that is in the graph. Last example is to determine the speed of a vehicle. Speed guns used by the PNP in Davao are actually taking advantage of the easy use of derivatives. When a speed gun is pointed and fired at your vehicle on the highway, the speed gun is able to determine the time and distance. With the use of derivatives, it is able to calculate the speed at which the vehicle was going. Not just that, of derivatives in various fields and sciences is also used in physics, biology, chemistry, and mathematics.
Hello. So we are going to talk about delta method. Before anything else, what is delta method? The delta method is a general method for deriving the variance of a function of asymptotically normal random variables with known variance. To further understand this topic, let's look at this example. So for our example, we'll be having f of x is equals to x squared minus 4x plus 3. For the formula, we'll be using lim as delta x approaches 0 is equals to f x plus delta x minus f of x over delta x. Solving this, Just simply substitute the x in the given problem with x plus delta x, and then subtract the new formula to the old given problem. Just like lim delta x approaches to 0 is equals to x plus delta x squared minus 4 x plus delta x plus 3 minus x squared minus 4x plus 3 over delta x. Perform the given operations and we'll have lim as delta x approaches to 0 is equals to x squared plus 2x delta x minus 4x minus 4 delta x plus 3 minus 2x plus 4x minus 3 over delta x. Since we have opposite signs in the problem, just cross that out and we now have 2x delta x minus 4x over delta x. Combine the 2x minus 4 and we'll have lim as delta x approaches to 0 is equals to delta x open parenthesis 2x minus 4 close parenthesis over delta x. Cross out the 2 delta in the numerator and the denominator and we'll have lim as delta x approaches to 0 is equals to 2x minus 4. And that will be our final answer for our given problem.
Let's talk about algebraic. The product rule states that if two factors raised to an exponent are being multiplied together and they have the same base, we can add the exponents. In this problem solving, we first identify the f of x and g of x. Negative 2x to the fourth minus 3 is our f of x. Negative 2x squared plus 1 is our g of x. Next, let's find our derivative of y prime or dy over dx. Using the product rule, we have to find first the derivatives of f of x and then multiply it by g of x plus the derivatives of g of x multiplied by f of x. Then we get the derivative of f of x, which is negative 8x cubed. Next, to multiply it to negative 2x squared plus 1. Then, add the derivative of g of x, which is negative 4x, and multiply it to f of x, which is negative 2x to the fourth minus 3. Next, we do the distributive property by distributing 8x cubed will give us 16x to the fifth minus 8x cubed. Then, distributing negative 4x will give us plus 8x to the fifth plus 12x. Lastly, we have to combine the like terms. Combining 16x to the fifth and 8x to the fifth will give us 24x to the fifth, then minus 8x cubed plus 12x. Therefore, the answer is y prime is equal to 24x to the fifth minus 8x cubed plus 12 of x. That's all for today. Thank you for listening.
Hi, I am going to discuss the trigonometric quotient rule. It is used in obtaining unknown angles and distances from known or measured angles in geometric figures. Here is the example of trigonometric quotient rule. Y equals cosine x over sine x plus 2. First, we have to find its derivative. The derivative of cosine x is sine x, and multiply using the denominator, which is sine x plus 2. Then the derivative of sine x is cosine x, and the negative sign is constant and put it on twice. Copy the denominator and put parentheses and squared. The next step is distribute negative sine x, so it would be negative sine squared x minus 2 sine x, and also the negative cosine squared x, and copy the denominator. For the last step, the equation should be in a parenthesis form, and if you're wondering why it is positive, because if you distribute the negative, the result would be the same in second solution, and it's like factoring. Just copy the denominator, and this is the final answer.
Now, let us try and solve higher order derivatives. But first, what are they? Well, higher order derivatives can be explained this way. The derivative of a differentiable function f, which is f prime, is still a function. Therefore, we can still find its derivative if ever it exists. Or in simple terms, we are able to find the derivatives of other derivatives. So let's have an example. Let us use this function of x, which is 2x cubed plus 4x squared plus 8x plus 999. So let's find the higher order derivatives of this function. So to do that, well, we just need to find its derivatives. So first, let us find the derivative of the function. So that would be the f prime, or the first order derivative. So to do that, we need to use the general power rule for the first three variables. And for the last variable, which is 999, we need to use constant rule. So through the use of general power rule, 2x cubed becomes 2 times 3x to the power of 3 minus 1. Then 4x squared becomes 4 times 2x to the power of 2 minus 1. And 8x becomes 8 times x to the power of 1 minus 1. And through constant rule, 999 becomes 0. So we are then left with 6x squared plus 8x plus 8. So since, as said earlier, this is still a function, we can then find its derivative, which is then we are able to find the higher order derivatives. So next, we are able to find the second order derivative. So just like what we did earlier, we need to use the general power rule. So 6x squared becomes 6 times 2x to the power of 2 minus 1, and 8x becomes 8 to the 8 times x to the power of 1 minus 1. And since 8 is a constant, it becomes 0. So we are left with 12x plus 8. Then we can find the third order derivative, which leaves us with 12 times x to the power of 1 minus 1 plus 0, which leaves us with 12. And since 12 is already a constant, by the time we are at the fourth order derivative, we are left with 0. So this is where it ends.
So, tips for future basic calculus learners. To fully grasp the concept of calculus, whether pre, basic, or any other different forms of calculus, it's always mandatory to listen. Listening and understanding are the most fundamental things to hold on to, especially when dealing with math-related subjects. Firstly, learn the basics of basic calculus such as the substitution and graphing, since these basics are what we would be doing in finding limits and in much more complex topics related to basic calculus. Another tip would be rechecking your answers, as one mistake is a crucial hindrance to the entire solution. This does not only apply to solutions but to graphs as well. Lastly, in a difficult subject like basic calculus, you need to understand how and when to be patient, as your mental capacity is very important before anything else. Not getting the answer as soon as you start one solution may be very frustrating. That is why this requires a lot of focus and patience. Basic calculus may be easy for others or may be hard for some, but always remember we stand on our own feet. So take it step by step, just like the solutions.